So the only way we can speed up the execution of a program is generally by using many processors, right? So that is called as parallel processing. But then if you have only one processor and if you want to speed up the execution, there is other way. So the technique is called as pipelining. Using pipelining, we'll be able to execute more than one instruction at the same time. So how it is done is, I'll better take an example and explain you. Let's see this example. Assume that in our processor, in our CPU, we have these phases. First one is instruction fetch and instruction decode, execute the instruction and write back the result. Assume that these are the four phases that we have in our instruction cycle, right? Now in general, if you don't have any concept of pipelining, as we have seen in our basic computer design, if you have to execute, let us say, 3 instructions. See, now I'm just taking some basic assumptions. Later we shall go into the depths and then see whether our assumptions are right or wrong. For now, I'm assuming that all the phases of the instruction pipeline are going to take the same time, and I'll call it a clock. Okay, so one clock, assuming that one clock is required to fetch the instruction, and one clock is required to decode it, one clock is required to execute it, and one clock is required to write back the result. But this might not be true in practice, and we shall see the questions where each phase in the instruction cycle will take different number of clocks, right? The reason is, fetching an instruction will depend on how long the memory cycle will take, right? And decoding will depend on how long can you load it into the processor and how long is it going to take to generate the control signals. And then execution depends on what type of operation it is. For addition and subtraction, it takes less time. For multiplication, it takes more time. Similarly, for integer operations, it takes less time, and for floating point, it takes more time. So exactly how much time is required for each phase, we shall see it later. For now, my assumption is that every phase of the instruction cycle is going to take the same time, and that time I am going to call it as one clock. Okay, we know that we are going to apply a clock to the processor, and depending on the frequency of the clock, we are going to have the time period for each clock, right? So this is what I am talking about. If you have the clock like this, clock is generating the pulses, this is called as one clock, right? And the time period of this clock depends on what is the frequency. If the frequency is 1 megahertz, then time period is equal to 1 by frequency, which is nothing but 10 power minus 6, which means 1 microsecond. Got it? So it means that in 1 microsecond, this is the time of the clock is 1 microsecond. In 1 microsecond, we will be able to perform any of these phases in the instruction cycle, right? So for now, let's not get into this exact number. Let's keep it this way. For every phase, it is going to take 1 clock cycle. Okay, so for one instruction, it is going to take 4 clock cycles, right? Okay, now how many clock cycles do you think will be needed in order to execute 3 instructions? If I have to execute 3 instructions, I need 3 into 4, which means 12 clocks. 12 clock cycles are required in order to execute 3 instructions, isn't it? Now, by using a method called as pipelining, we'll be able to speed this process up. Okay, so I'll explain you how it is exactly done. See this, I'm going to draw here a diagram which is called as phase time diagram, right? Phase time diagram. So in order to do this, first of all what happens is, we are going to split up the CPU or the hardware in the CPU into various functional units, and we dedicate each unit for each phase. For example, we will dedicate or designate one particular unit of the CPU to perform instruction fetch, and similarly one particular unit of CPU to perform instruction decode and instruction execute and write back, which means I am assuming that in our CPU we are able to divide the combinational circuit into further smaller units in such a way that each unit will be able to take care of each phase, right? And by having such things, we will be able to get the parallelism. Okay, so how to divide it, we shall see later. What are the penalties that we get, or what are the other trade-offs that we have to undergo because of this particular dividing the entire CPU into various functional units, that we shall see later. Now let's see how to execute the instructions in a pipeline manner when we have different functional units, each taking care of each phase. So I'm going to have 4 phases here. Okay, so what are the 4 phases? Instruction fetch, instruction decode, and execute the instruction and write back. These are the phases, and here I am going to write the clocks. So this is clock 1. So how do I know that it is clock 1? I am just assuming that if I start from this clock, I am just numbering that clock as clock 1. Actually, we cannot know whether it is the first clock or second clock or third clock. It is just relative, which means if I start from now, I'll assume that the current clock is the first clock. Clock 1, clock 2, clock 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Again, so on. Now, why did I stop exactly at 12 clocks? How do you know where to stop? That actually depends on the options given in the question. In the question, if you see that some option is given as 15, then you have to go till 15 clocks. If they give it as 20, you have to go till 20 clocks. There is no other option, right? Here, I know that it is going to take probably 12. That is why I stopped it there. Okay. So see, why did I stop at 12 is simple. We are already assuming that we are going to execute, for 3 instructions we are going to take 12 clock cycles. Here I wanted to see for the same 12 clock cycles how many instructions I will be able to execute. That is the only reason. Okay, so when we take up the questions, I will explain you clearly how to draw this diagram. How many clocks you should take it. Okay, and now you don't do this in the exam. Here, for the sake of explanation, I am going to do like this. For all the questions, I will be putting up the boxes just to make the things clear and visible for you. When you are doing it on the page with paper, with paper and pen, it will be very clear that you don't have to do this, all these boxes. It will just waste your time in the exam. Okay, when you are practicing it, or in case if it is very difficult for you to work without these boxes, then go for it. But my suggestion is don't do this in the exam. It might take up a lot of time. Okay, now at clock 1, I'll put instruction 1 in the instruction fetch phase, which means the functional unit which is dedicated to fetch the instruction will now be fetching instruction 1, right? Now after this, once the clock 1 is over, it means that instruction 1 is already fetched. Therefore, I can send instruction 1 to the next functional unit, which is instruction decode. Once the instruction is fetched, it will be sent to decoding, right? I1. Now I1 at clock 2 is at instruction decoding. Now if you watch it, at clock 2, I1 is in decoding, but the fetch phase is idle. So why do you want to waste it? So this is where the parallelism comes into picture. This is the advantage of pipeline. So even when I1 is still under execution or under processing, we are able to start I2. That is the entire concept of pipeline. So even if the present instruction is currently under processing, we will be able to start the next instruction. That is called as pipelining, right? And now by the end of the second clock, first instruction is done with instruction decode, therefore it can start execution, right? Similarly, second instruction is done with fetching, so it can do instruction decoding. Similarly, at the same time, at the clock 3, if you see the functional unit instruction fetch, this fetching unit is completely idle. So why to waste it? You can start I3. This is the power of pipelining, right? At the same time, earlier there was only one instruction which is being processed. Now there are 2 instructions. Now there are 3 instructions which are currently being processed. Now after the completion of the third clock, I1 has completed its execution, therefore it can go into the write back phase. Similarly, I2 has completed its decoding, therefore it can go into execution, and I3 is done with the fetching, therefore it can go with decoding. And now this one is idle, so you can fill it up with I4, which means you can call I4 for fetching. So if you observe this, at the same time during one clock we are actually processing 4 instructions simultaneously. This is the power of pipelining. We are actually able to do many instructions at the same time. Now in case of normal execution, let us say it is not the pipeline execution, then what happens is at any time only one instruction will be working, right? Only one instruction will be processed, but here at a given time 4 instructions are currently being processed. This is the power of pipelining. Now I'll just fill it up first. Okay, now I4 is out, which means I4 is completely done at 4th one. Now if you see this, I2 will be here, I3 will be here, I4, I5, right? I3, I4, I5, I6, I4, I5, I6, I7, I5, I6, 7, I8, I6, I7, I8, I9, I7, I8, I9, I10, I8, I9, I10, I11, that I9. Okay, so let's assume that we have only 9 instructions to execute, and let me not execute I10, I11. So let's say I have only 9 instructions, and now if you observe it, watch this one. If you observe it, by the end of the 4th clock, I1 has finished its execution because it needs only 4 clocks, isn't it? Similarly, by the end of the 5th clock, I2 has finished. By the end of the 6th clock, I3 has finished. So which means for the first instruction to come out of the pipeline, it has taken 4 clocks, and after that for every clock we are able to get one instruction out. That is the main aim of pipelining, right? So what is the advantage of pipelining? We'll be able to execute many instructions at the same time. What is the aim of pipelining? We want to execute the instructions at a rate of 1 instruction per clock. So this is called as CPI, right? So the main aim of pipelining is to maintain CPI close to 1. It is practically impossible, but this is what we try to do, right? The main aim of pipelining is to see that the number of clocks required per instruction should be equal to 1. So if you observe this, here in this case we have taken 12 instructions, I mean to say 12 clocks, right? But then if you try to understand this, after 4th clock first instruction has come out, and from there on for every 1 clock 1 instruction is coming out. Therefore the number of clocks per instruction is close to 1, right? And there are various ways to measure the performance of pipelining, right? So some people also will try to write this CPI equal to 1 in some other form. So what they will say is, see, one instruction has taken 1 clock, right? Now we know that the time taken for this 1 clock is nothing but 1 by f, right? 1 by f seconds, isn't it? Therefore in one instruction has taken these many seconds. So how much in 1 second how many instructions can we execute? In 1 second we can execute f instructions, right? So in 1 second how many instructions can we execute? That is also going to be a measure in order to talk about this. So how generally what we say is, in any pipeline the clocks per instruction is going to be so and so, or sometimes people will say in 1 second we are able to execute these many instructions in our pipeline, right? and some people will also talk about it in million instructions per second. How many million instructions are you able to do it per second, right? So there are various ways we can talk about it. Okay, and now we'll try to find out what is the performance of the pipeline. So the next interesting question on this one is, what is the performance, right? Aim of the pipeline is to maintain one clock CPI equal to 1, right? But then how are you going to measure the performance? So performance is going to be measured using two factors. One is called as speed up, and the other one is called as utilization or efficiency, right? So I'll just tell you here what is utilization or efficiency. Utilization or efficiency of a pipeline. So once you draw this diagram, this is called as phase time diagram for a given load. So in this case the load is 9 instructions, right? So this one is given for 9 instructions. And always remember, when you are talking about utilization or efficiency, we generally talk about it given a load, which means for 9 instructions this is the efficiency, for 100 instructions this is the efficiency. That is how we talk about it, right? So in this case the utilization or efficiency is, you see all the boxes. How many boxes are there? So 1 2 3 4 rows and 12 columns, therefore 12 into 4. Total number of boxes is going to be 12 into 4, right? And out of this, how many boxes are utilized? So 12 into 4 is 48, right? So how many boxes are utilized? Let's see how many boxes are not utilized, right? Which means this is inefficiency, isn't it? See, you could have used this space also, but then you are not able to use it, because unless you finish this I1's fetching, you cannot start I2's fetching. Therefore you will not be able to fill it up directly, which means pipeline will be filled up gradually. It will not be filled up directly with all the phases, right? So all these 6 are wasted at the beginning, and at the ending these 6 are wasted, if you see it, right? So 48 minus 12 is 36. So out of this only 36 slots are used, right? And the remaining are not used. So efficiency is nothing but out of the total, how many are you able to use? So out of 36 you are able to use only 48. Sorry, out of 48 you are able to use only 36, which means the efficiency or utilization is 3 by 4, right? And this is one way they might ask you the question. Given the load, they will ask you the efficiency, then you can say like this. And the other way is they will ask you speed up. What is the speed up? So speed up also can be asked in two ways: when load is given, when load is not given. In this case, assume that load is given. What is the load? 9 instructions. In order to execute these 9 instructions, when we execute these 9 instructions this way, like this, then what is the speed up we got here? So that is nothing but, speed up is nothing but time taken without pipelining divided by time taken with pipelining in order to execute these 9 instructions. In case if you have 9 instructions to execute and if you don't have a pipeline, then how much time will it take? 9 into 12, 9 into 4, isn't it? Divided by how much time did it take here? 12, right? So it is 36 by 12, which means 3. So speed up in this case for a load of 9 instructions given this 4-stage pipeline, right, is actually 3 here. Okay, so by looking at this you can derive a relation between these two, speed up and efficiency. In general, the efficiency equal to speed up equal to efficiency into this one, right? So m into, you can say like this, m into efficiency equal to speed up. Yeah, so you can check this. So this is the relationship between these two. Speed up is equal to m into efficiency, right? So by looking at this, you can say one thing: the maximum value of speed up we can get is equal to number of stages, where m is the number of stages. Okay, so in this case m is the number of stages, which means 4. If you want, you can check it out. See this. So speed up, this m is 4 into efficiency is 3 by 4 is equal to, of course, 3 speed up, right? So it is satisfied. Now you can check this one. Speed up is going to be the number of phases multiplied with efficiency, and now if you look at this efficiency, the value of this efficiency will be anything between 0 to 1, right? Which means if you are going to have 100% efficiency, then speed up will be equal to m. So in the question they might ask you this. Let us say the utilization of a pipeline is 100%. Then what is speed up? Then the speed up is going to be number of phases, right? In case if they say like this, if the efficiency is 75%, then what is the speed up? Then we have to know what is the number of stages. Then depending on the number of stages in the pipeline, you multiply that with 0.75, right? But one thing is very clear here. Always, see, in practice we'll never get 100% efficiency, isn't it? You can see it clearly. Here some of it is wasted and here some of it is wasted, right? So we might go close to 100%, but we might never get 100% efficiency, right? So as long as this figure is not equal to 1, our speed up will never be equal to m. Therefore in practically always speed up will be less than m, right? But in theory speed up will be almost close to m, right? So we shall see why it is so. I think you understood this one, right? So let's keep this apart and let's talk about the speed up. So how to derive this speed up in some other way. Now, so if you observe this, how did we get this 12 clocks for 9 instructions? Observe this closely. The total time taken here is actually the time taken for 9 instructions, and we got this time to be 12 clocks. How did we get this? If you observe it, the total time taken, we can write it like this. For the first instruction, see this, for the first instruction the time taken is 4 clocks, isn't it? For the first instruction to come out, the time taken is 4 clocks, and then for the remaining 8 instructions, 1 clock for every instruction, it is taking only 1 clock, which means for every 1 clock 1 instruction is coming out, right? So therefore we got 12. This is how we got 12, isn't it? Now assume that we have to execute large number of instructions. Let us say n is the total number of instructions, large number of instructions that I want to execute. N is the total number of instructions that I want to execute. Then what is the total time taken in case if you are having pipelining, right? So time taken if I go with pipelining for n instructions is equal to, for the first instruction always I have to wait for the number of clocks, which should be equal to the number of phases. Let us say m is the total number of phases. Instead of 4, I am just using the number m, okay? Plus first instruction is going to take m clocks, and for the remaining n minus 1 instructions, one instruction is going to come out every clock. Therefore this is the total time taken in order to execute n instructions in a pipeline manner. Now without pipeline, what is the time taken to execute these instructions without pipeline? If you go without pipeline, then what is the time? If you don't have any pipeline, if you have to execute 10 instructions, assuming that every instruction is going to take m stages, it is going to be these many clocks. So this is the total number of clocks required to execute n instructions with pipelining. This is the total number of clocks required to execute the n instructions without pipelining. Then what is the definition of speed up? The definition of speed up is time taken to execute without pipelining divided by time taken to execute with pipelining for a given load. Now here I am assuming that the load is n instructions, right? Then what happens here? Here it is going to be m plus without pipeline n into m, right? N into m divided by n plus m minus 1. I just rearranged the terms. See this is nothing but m plus n minus 1. I just wrote it like this, n plus m minus 1, right? And now you divide numerator and denominator with n. If you divide numerator and denominator with n, then what do you get? M divided by 1 plus m minus 1 divided by n. This is the speed up factor, right? Now let's see what happens if the number of instructions is infinity, which means we are going for a very large number of instructions. See, infinity is never possible. We can never execute infinite number of instructions, but assuming that n is very large, right? As n becomes very large, as n tends to infinity, what happens to this speed up? Speed up will become m divided by 1 plus some constant divided by infinity. See, m is a constant here, which means m is the number of stages. M divided by 1 plus something divided by n, right? So where n is a large number, so this entire factor is going to become 0, and so speed up is going to be close to m. As n becomes very large, speed up becomes close to m. Therefore, in theory, speed up is going to be equal to the number of stages. But in practice, speed up will never be equal to the number of stages, because n will never become infinity, and this entire factor will never become 0. This entire factor will become something close to 0, right? And therefore 1 plus something close to 0 is nothing but this entire thing is going to become something less than m. So S should ideally, if we talk about theory, yes, it is going to be equal to the number of stages, but then in practice it is not going to be equal to the number of stages, right? So it is going to be less than the number of stages m. So speed up is always less than m. So if you want one more reason why the speed up may be less than m is simple. See this, the time taken to execute one instruction without pipeline may be less. So if you assume like this, the time taken to execute an instruction without pipeline, let's say is this one, this time will be less than m into clock time taken to execute p. So this is somewhat difficult for you to understand. I don't know if you are getting this or not. I'll just try explaining it. If you don't understand this part, skip this video. It is okay. If you understood till here, it is okay. Now let's try how this is right. See, what happens is, when we don't have this pipelining, the CPU is completely one single combinatorial circuit, right? Now when we try to get this pipelining into picture, we try to divide it into various functional units, and then we try to place buffers or registers between every unit, right? Therefore, as a result, the time taken to execute an instruction in the pipeline, m into this one, will be greater than time taken to execute it without this. Are you understanding this? In case if you don't have pipelining, entire CPU is going to be one single combinational circuit. In that case, what happens is, your instruction will start here, and without any restriction or without any stopping, it will complete its execution smoothly. But with the introduction of pipelining, we have to divide this entire combinational circuit into many smaller units, and between every unit we are supposed to place the resistors or buffers, which are going to take which are going to give some delays, right? Because of which the time taken to pass a single instruction through all these phases is going to be more with these added delays, right? So time taken to execute without pipelining is less than m into tp, isn't it? Now if you see this, if you observe this one from this equation, time taken to execute without pipelining divided by with pipelining is less than m, right? Now we know that this factor is nothing but the speed up, therefore speed up is less than m. Got it? So anyway, ideally we should closely approach to the number of phases. Now I think you understood what this speed up is. Speed up is nothing but how much faster we are going to do it. See, I'll just tell you, speed up means how much faster we are able to do it. That is the meaning of the speed up, right? So in the earlier case, for this example, for this particular example, we are able to execute 9 instructions in 12 seconds or 12 clocks. 9 instructions, it took 12 clocks in pipelining, right? But the same 9 instructions without pipelining has taken 9 into 4, which means 36 clocks. Therefore, we are able to execute it 3 times faster with pipelining. That is the meaning of this speed up. Speed up says how much faster will you be able to execute it, right? 3 times faster. We are able to do it 3 times faster, right? Now this equation says that with enough number of instructions, if you go on increasing the instructions, our speed up might reach 4 times faster, which means this one is saying that we might be able to go to a speed of 4 times, right, maximum. So why is this so? Why will we be able to reach 4 times faster? Is because at any time, if you observe this, in most of the phases we are able to execute 4 instructions at the same time. That is why we should be able to get the speed up as 4 times faster. We should be able to do it, right? Now what does efficiency said? Now we found out that efficiency was actually 3/4. So what did it say? It is saying that our pipeline is capable of executing the instructions 4 times faster, but we have used it in such a way that we are able to execute it 3 times faster only. That is what efficiency has said, 3/4. Got it? Okay, anyway, if you are not able to understand it, just by heart it. So what I mean to say is, our main aim of having this pipelining is 2 things. First one is to maintain the CPIs, clocks per instruction, as 1, and the second one is to have a speed up equal to the number of stages. You might get one doubt. If we increase the number of stages in the pipeline, we are getting the speed up very high. Then why can't we increase it to a very large number? In practice, most of the computers, they are using a pipelining ranging from 3 to couple of dozens, 24 stages. Right now our present computers are able to go till 24 stages in the instruction pipeline, 24 stages, right? But beyond that, when we go, there are various factors like cost. One is cost is going to increase, and the other thing is other delays will additionally add up, which will degrade the performance. That is why people are not going beyond this 24. Anyway, the maximum limit, and also there have been some experimentations which prove that 5 is the best number. 5. There have been some derivations and experimentations which prove that if you go with 5 instruction, 5 stage pipeline, it will give you the best performance. Okay, fine. So this is what is about the main aim of pipelining. But then, because of various reasons, we will not be able to reach this particular thing all the time, especially this one. Our main aim is to see that the average number of clocks required to finish an instruction should be 1, but then there are various reasons why we will not be able to do that. So one reason is there are various things that they are called as dependencies, right? So there is something called as data dependency, control dependency, structural dependency, right? So these things are going to affect the performance of the pipeline, and we'll be able to overcome them somehow by using certain techniques, and these techniques might not be useful in all the cases. We'll see in detail what these are and how to solve them. If you see that is the concept of pipelining. Okay, fine.